Capacitor Basics. The title of this webinar is So You Think You Understand Capacitors. And let me begin by introducing myself first. My name is David Adib, and I will be your host today. And our presenter today is Mr. Wilmer Companioni, and he is our Senior Technical Marketing Manager. And with that said, I will turn it over to Wilmer. And Wilmer, please go ahead and introduce yourself to our audience, and you can get started with your presentation. Thank you.
All right. Thank you, David. And thank you, everybody, for joining this latest session in our global webinar series, all about understanding capacitors. And we're going to get into some of the basics and not so basic aspects of capacitors. And as David said, my name is Wilmer Companioni, and I've been with KEMET for the last 6 years, and I have a background in electrical engineering. And I wanted to put together this webinar to try to get us all to a common frame of reference, what it is that we're talking about capacitors, and what are some of the common themes, common terms, and challenges when an engineer is designing with capacitors. And hopefully what you get out of this, even if you're a seasoned and experienced engineer, is the clarification of a few things that may have been left a little bit nebulous when engineers are getting up to their studies in electronics and design. Many times capacitors and other passive components are sort of brushed over fairly quickly. And they are perhaps the most common electronic component as far as individual components goes. And they don't get a whole lot of service. And that's understandable because there's many, many other components that have much more critical functions in the circuits themselves. But so it's understandable why maybe some of it is not understood as deeply as other things, but we're going to try to dispel some of those things today. We're going to try to dive into some of those things today. So today, as I said, we're going to cover what is a capacitor, the definition of capacitance, which sounds a little bit philosophical in the way, especially when the early definition is just, oh, it's the ability to hold charge, but there's actually much more to it than that. Then we're going to get into some of the physics of dielectrics. What makes a dielectric different than other materials? And then we're going to talk about capacitor parasitics. So what are some of those non-ideal effects, where they come from, and how they can possibly impact the circuit? Then we're going to take a look at electrical response of a capacitor. So what actually happens inside to currents and voltages as you energize, in a way, a capacitor. We'll do a quick demonstration, an RC circuit that I'm sure many of us have seen before, but we're still going to talk about it because that's a nice way to round out this conversation. And then we'll get into a recap of the key takeaways. So what is a capacitor? The almost dictionary type of definition of what is a capacitor is that it is an energy storage element that holds energy in its electric field. So from a construction standpoint, all it is, very simply, it can be modeled using the so-called parallel plate model. So you have two parallel electrode plates separated by some distance, and in between those two parallel plates is what's called a dielectric material. And the overall capacitance in that type of model can be estimated using this equation here. So the overall capacitance is epsilon naught, which is the permittivity of free space. And we're actually gonna get into what does permittivity mean. Then multiplied by the relative permittivity, sometimes known as the dielectric constant, or K. So it's the relative permittivity of the dielectric material, and then the surface area of the two electrode plates. And that's a critical component to capacitors. So there's several things you can play with when you want more capacitance, if you will. You can pick a material that has higher relative permittivity. You can increase the area of your electrode plates, which many times necessarily means that you increase the size of your capacitor, the physical size of your capacitor. And then you can minimize the distance between the electrodes. Now, minimizing the distance between the electrodes has the impact that as you shorten that distance between the electrodes, your capacitor can actually hold less voltage, because as those electrode plates get closer and closer together, you can actually break down the dielectric between them. So from a physics standpoint, the closer those electrode plates are, the less voltage rating that capacitor has. So as I said, capacitance is the ability to store charge. So when voltage is applied, charges build up on the anode plate, and then opposing charges build up on the cathode due to electrostatic repulsion. And many times you can represent the capacitance as charge over voltage. So in essence, you can think of it as I'm holding a certain amount of charge at a certain voltage, and that is the capacitance. So internally, well, let's get into this. So it's the ability to hold charge. So internally, what happens to a capacitor after you hold charge, the electric field there remains after the external voltage is removed due to that built up charge. And then it will actually, the electric field will actually decay slowly over time as those built up charges will dissipate due to leakage. And one of the things, one of the results of that is that a capacitor actually opposes changes in voltage. So once you store all those charges, once you put all those charges on the electrode plates and you have that charge separation, they'll remain there. In an ideal capacitor, they'll remain there indefinitely. In reality, there is a mechanism called leakage that will cause those charges to decay over time. So they'll sort of leak out they'll flow from the anode into the cathode, and the capacitor will eventually be discharged. So let's take a closer look at the physics of dielectrics. So what happens internally to that dielectric material when voltage is applied? So you apply the voltage, that builds up the charges on the electrode plates, and then this is where the distinction of a dielectric and an insulator come into play. What happens in a dielectric is that there are what are called dipoles, and the dielectric is not a typical insulator. Yes, it is an insulator in that it doesn't conduct electricity. However, that dielectric material internally has dipoles that can then align themselves to an external electric field. So they will polarize in the presence of an external electric field. Not all materials do this. So it's not enough to say that any insulator makes a good dielectric. So you can't really make a capacitor out of some type of rubber or other dielectric material, because that dielectric material won't polarize. And permittivity is actually a material's ability to polarize in the presence of an electric field. So what does it look like when that dielectric material polarizes? Those charge carriers, if you will, they're not really flowing, but there is an electric dipole, an electric separation of charge. They will actually line up in the presence of an external electric field. So that means that the material has the capability of spontaneously generating these dipoles and aligning to the external electric field. So that, in essence, is the internal physics of dielectrics. And that's where all this capability to store charge comes from the fact that the internal dielectric material has become polarized. And that's a critical component. And as I said, permittivity is a measure of a material's ability to polarize in the presence of an external electric field. So let's do a quick poll question here, now just to recap some of the knowledge that we've learned. So where is the charge of a capacitor stored? So I'm going to launch the poll question here. So where is the charge of a capacitor stored? Is it on the parallel plates? Is it within the polarized dielectric itself? It's not really storing charge, so we'll give us a couple minutes to do this, to get to this, couple of seconds to answer this poll question. So I'll share the responses here as soon as we close the polling. All right. So I will share the results. All right. So this one is a bit of a tricky question. So we had 26% said that the charges are stored on the parallel plates. And then we had a large portion, almost 70%, saying that it's stored within the polarized dielectric. Now, I wouldn't say that the people who said that it's stored on the parallel plates are wrong in a sense. That is sort of the very beginning of it. But ultimately, a more right answer is it's stored within that polarized dielectric. Once that dielectric becomes polarized, that's essentially what causes this storage and this separation of charge. So let's move along. So at the end of the day, actually, a capacitor is not really just a capacitor. An ideal capacitor sure would have perfect permittivity, if you will, and it would have zero leakage, and it wouldn't have any of these other parasitics effects. But in fact, it has other things. So any one capacitor you buy actually is 3 passive components in one. You have an ESR, an equivalent series resistance, that comes from the dielectric losses and those metal losses. You also have, of course, the main capacitive element itself, as well as an inductor that comes from the self-inductance of some of the metal within the capacitor. It could be the electrode plates or also the terminations of the capacitors. So these 3 things all combine together to form a more accurate representation of what a capacitor is. Now, impedance is the opposition to electrical stimulus that comes from several components: the reactance of the inductive element and the capacitive element, and those affect, you can think of those as affecting the AC portion of the signal. And then those opposed changes, the reactance together, the capacitive reactance and the inductive reactance come together to oppose changes in current and voltage. Then the resistance, which comes from the ESR, is an opposition to the flow of DC current. So you can think of almost the resistive portion of this, of impedance, as an opposition, as affecting the DC portion of a signal. And then impedance is a complex number. So that simply just means that it can be represented as a vector. Resistance and reactance are orthogonal to one another, but they combine together to form that vector that we know as impedance. And an interesting thing happens at a particular point in frequency of a capacitor, or really any passive component. And that happens when the capacitive reactance and the inductive reactance are equal to each other, and they cancel out. And the only thing you're left with is the real portion, or the ESR, of the capacitor itself. And you can actually estimate some of those effects using our simulation tool, KEMET. So this very sharp V type of curve is very distinctive of the impedance signature of a capacitor. It comes to that low minimum point there, and that's the self-resonant point, the point at which your capacitive reactance and your inductive reactance are equal to each other. And then the overall impedance is equal to the ESR of the capacitor. So it's just the real portion. That's why at that point, the impedance curves and the ESR curves meet. So let's take a bit of a closer look at ESR. What are some of those mechanisms that result in equivalent series resistance? So once again, I'm applying voltage to this capacitor, and that has the charge separation built up on the electrode plates. And then that causes the dipoles to start to align. But in reality, not all dipoles in a dielectric material will fully polarize. They actually exhibit some resistance, or really some almost like reluctance to polarize. And that's one of the mechanisms that gives rise to ESR. It's a loss mechanism. So if you think of it from an energy standpoint, the energy in a capacitor is 1/2 capacitance times voltage squared. But in a real world, as usual, we have to obey the laws of thermodynamics, and you can never get as much energy out of something as you've put into it. There is always a loss. And one of the things we use to measure that amount of loss is the dissipation factor, which is described, it's defined as a ratio of the ESR at a particular frequency divided by the capacitive reactance. You can also do a little bit of math, and it comes out to that the dissipation factor is the capacitive reactance, or 2 pi FC, so 2 pi F times capacitance times the ESR. So then if you use that dissipation factor, the energy out of a capacitor is actually 1/2 CV squared times 1 minus the dissipation factor. You can almost think of it as a measure of the efficiency, or I guess in this case, inefficiency of a capacitor. And in general, you want to keep that dissipation factor very low as you can, because then you have a less lossy capacitor, more of an ideal capacitor. Of course, because of, as I mentioned, you can never get as much energy out of a system as you put into it. There's always going to be some measure of dissipation factor to a capacitor. So what happens to a capacitor when it's charged? At the instant I apply voltage to a capacitor, it acts short. And then as time goes on, the capacitor acts open. And you can actually describe that using a couple of mathematical equations as the current is equal to capacitance times dV dt, so the change in voltage over time. So if you have what is essentially an instantaneous change in voltage over time, like when you close the switch on a capacitor, that will result in a spike in current. And then if you take that in this particular case, if you take that into account along with Ohm's law, which is voltage times resistance, in this case ESR, you do some differential equation magic, you come up with an equation that describes the voltage of a capacitor over time. And it's this very distinctive exponential rise and decay. So there's the, let me turn on the laser pointer here. There's that instantaneous rise in current right here in red. And then as time goes on and the capacitor charges, that current decays. And then the voltage also starts to come up in a sort of logarithmic growth pattern, if you will. And then there is a factor known as the time constant. The time constant is the multiplication of the resistance times the capacitance. And it's actually a number that comes out to, as you do all the math of the units and the cancellations and everything behind it, it comes out to seconds. So when at a point in time where t is equal to tau, so is equal to the time constant, the capacitor will have charged to 63.2% of the voltage that you're charging it to. And after several time constant time intervals pass, that capacitor will reach full charge or close to full charge. But after one time constant, you will get to 63.2% of the target voltage. So let's do a quick demonstration and a poll question, or a poll question first, followed by a quick demonstration. So let's say I have this circuit here, a very typical circuit, almost a first-year circuits type of circuit. You have a known resistance, known capacitance, and I put a square wave into it. The poll question is, what will I see on the output here? So let me launch the polling. So what will happen in this circuit? Use the poll window to answer. So will the signal pass through? Does it depend on frequency? Will it turn into shark fins, as it's called? Or, I wasn't paying attention. I minimized the Zoom window and I got to doing some emails. All right. I think that's enough time there. So I'll share some of the results. So as usual, there's a little bit of trickery here. So those of you who answered that it depends on frequency, yes, that is true. It very much does depend on frequency. If you think back to the equation for impedance of a capacitor, as frequency goes up, in this case, the impedance of this thing starts to decrease, of the capacitor starts to decrease, which means more of that AC portion of the signal will actually be shunted over here to ground, will be coming this way instead of passing through that way, because as we all know, electricity and water and gas and many other things always take the path of least resistance, least impedance. So it wouldn't necessarily pass through. It does have a dependence on frequency. Now, those of you who answered that it will turn into shark fins obviously have done this experiment before, because that is exactly what happens. And I'll show this right now in a quick demonstration. So I'll be switching my screen here to my window. And let me change my setup. So what I have here is exactly that circuit that I just described. The circuit with the resistor and capacitor. And what's happening, the yellow is the input, and you can see that the output here in red is rising in that sort of inverse exponential format. And I have my cursors here set up to where the voltage is 63.2% of the target voltage. So I have my output here at 5 volts. 63.2% of 5 volts is 3.16 or so. And then that time is 10.49 milliseconds. So if you do that RC time constant math, it all sort of checks out. There's a little bit of variation here because of tolerance, because this is a non-ideal circuit, and there's other things that are not being taken into account. But generally, yes, that's what happens. So those of you that mentioned that the output of this circuit is going to be shark fins, in the red, you can sort of see those shark fins rising and falling with a bit of a delay to what the original input was. Now, those of you that said that it depends on frequency, you're also right. That's definitely true. So what I'm going to do now is I'll change the setup here to go at a faster frequency. Right now, I'm only going at 10 hertz, so rather slow. So slow enough that this capacitor has enough time to charge almost fully and discharge with every cycle of this waveform. But when I go at a high enough frequency that the capacitor doesn't really have time to even charge or discharge or respond, that's where you get into that low impedance scenario. And the the input now is coming in at 10 kilohertz, so 1,000 times faster. And the voltage across the capacitor is, or at least you're not seeing anything on the output. What you're actually seeing is this 2.5 volt offset. That's because the only thing that this circuit here is passing is the DC portion of the signal. I have my function generator set up to go from 0 to 5 volts with a 2.5 volt offset. So a nice little square wave from 0 to 5. And it's just passing the DC offset. So the capacitor's impedance has gone low enough that the high frequency portion of the signal is all getting shunted to ground, and the only thing passing through is the DC offset. This circuit is what's known as a low pass filter, very basic circuit in electronics, and it's used all the time. To create different configurations of filters, you can swap the position of the resistor and the capacitor and you'll get a high pass filter. So at low frequencies, you'll see this flat, and at high frequencies, you'll actually see those so-called shark fins. So let's go back to our presentation. Okay, so let's do a quick recap here. And let's recap the things that we've covered in this particular webinar. Number one is capacitors are energy storage passive components. And it depends on the relative permittivity of your dielectric material, the surface area of your electrode plates, and the separation between those electrodes. Then dielectrics are materials that become polarized in the presence of an external electric field. So not like your usual true insulators, these dielectrics have the ability to polarize in the presence of an external electric field. And finally, real capacitors are not ideal. They have several parasitic effects that affect the operation of your circuit. They have an equivalent series resistance that comes from dielectric losses and metal losses. They have their main capacitive element, of course, and then they have what's known as the equivalent series inductance, or ESL, which comes from the self-inductance of the metal components made to build the capacitor. So the electrode plates and a large portion of it comes from the terminations, the termination materials, the leads, the things that you use to connect the capacitor to the outside world. So if there are some questions now, David, we'll take them through the Q&A window. We'll leave about 15 minutes for questions or so, and then we'll wrap up very quickly after that 15-minute portion of questions. So okay. David, I'll take some questions now.
All right, sounds good. So the first question we received says, if you have an air dielectric, how is charge stored in an air dielectric capacitor?
So all materials have the capability to polarize. As I mentioned that, let's see if I can go back far enough. Okay, as I mentioned that dielectrics are different than regular insulators in that they have the capability to polarize. All materials actually have that capability. The higher the capability is known as higher permittivity, which means that it has a higher tendency to polarize in the presence of an electric field. So everything does, even a vacuum. That's why you have the permittivity of free space. It's actually a very, very small number, but still it's there. And so does air. So if you have, let's say this dielectric material here in the gray was air, this capacitor is going to have a certain amount of capacitance. And if you keep all things the same, you replace the air with something else that has an even better propensity to polarize, then your overall capacitance goes up. So in essence, yes, if you have an air capacitor, it's still polarizing, just much less so than a better dielectric like a ceramic or something like that.
Okay. And before we move on to our next question, let me just remind our audience that if you enjoyed today's webinar, you're welcome to join us on Wednesday of this week, where we'll be talking about the ceramic and film construction of capacitors. And next week, Monday, June 8th, we'll be talking about tantalum and electrolytic construction characteristics of a capacitor. So with that said, let's move on to our next question. The question says, I wonder if there is a formula that connects the dV/dt properties of a capacitor to the physical dimension in terms, I think he meant in terms of D and A of the capacitor and dielectrics properties.
I think there is. I don't. That D and A, that the distance and the distance between the electrode plates and the area of the electrode plates, if you were to know them, whatever they are from your capacitor manufacturer, if they were somehow able to tell you, yes, this capacitor has a dielectric separation of 1 micron and has 17 centimeters squared square centimeters of area, you could use this, one more time, this equation here, and then plug it back into the one here, and then it's all part of the same thing, right? Then you've kind of really broken it all the way down to the physical elements of a capacitor.
Okay. The third question says, how can we calculate the amount of inrush current a capacitor is going to take?
Calculate the amount of inrush current.
Mm-hmm.
Yeah, that is a good question. I would say it's probably, it's dependent on that dV/dt portion. So that's this section I have here, right? It's how much is your voltage changing over time. If you can, and many times you can actually find that out from the operating device, sometimes known as the slew rate. If you can get a sense of that, in many ways that is the inrush current right there, is how far up that current will spike. So multiplied by the capacitance. So in order to effectively do that, you have to know essentially how quickly you're turning that voltage on.
Okay. And our next question says, can you relate the plates aspect of with the construction of a ceramic capacitor?
So in a ceramic capacitor, and we'll actually get into these details, as David said, in our webinar on Wednesday. Wednesday we'll go into, among other things, we'll go into the construction of these multi-layer ceramic capacitors. But very quickly, multi-layer ceramic capacitors are exactly that. They are almost the closest thing to these parallel plates. They are, you have a set of electrode plates coming from one of the termination sides of an MLCC, and then you have the opposite electrode plates coming from the other side of the MLCC, and they form this sort of interdigitated, interleaved pattern from one another, and that's where these parallel plates are coming up. So they have these alternating positive, negative plates stacked up. And we'll get it. I didn't prepare that for this particular presentation because I wanted to try to keep it a little bit dielectric and technology agnostic. But in our presentation later this week and going through the rest of the month, we'll actually get into those details of construction and characteristics of the different capacitor technologies.
Okay. And our next question is an interesting one. Is KEMET simulation tool that you use open domain tool?
Yes, it is. So
yes.
That I mentioned, yeah, I'm sure you could have answered that one too, David.
Yeah.
The tool that I mentioned here is known as KSIM, and you can actually follow this link to this very simulation, in fact. So it has the capability of saving the simulations that you set up. And yes, it's available. Simply navigate on any browser, well, any modern browser, not Internet Explorer 6, please, to ksim3.kemet.com, and you can start simulating the behavior of many of our capacitors, and we're starting to introduce some inductor performance characteristics as well.
And not only that, but let me add that we actually just launched the new KSIM tool on May 11th, so just 3 weeks ago or so. So you'll be the person who asked the question. You'll find a lot of nice features that you can actually use that we're offering to our audience for the first time. Our next question says, what sort of performance trade-offs should we be considering as we move to capacitors with higher capacitance, between parentheses, higher permittivity?
Yeah, so that's a good question. There's always a trade-off, and many times I tell people that engineering is just the careful balancing of these trade-offs with your design requirements. So this is a bit of a rule of thumb, and it changes somewhat as you go from different capacitor technologies, but generally, the more voltage you have, the less capacitance you have. And that comes up from, I'm gonna have to go all the way back to the beginning. That comes from the fact that the dielectric material can break down in the presence of applied voltage. So well, I'll find that slide in a minute. So in general, though, the more capacitance you have, the less voltage you'll have. So if you take an equivalently sized capacitor, if you will, and increase its amount of voltage, then you'll lose its same capability of capacitance, because you think of it from an energy standpoint. You're building up quite a lot of energy in that charge separation between the electrode plates, and at some point that energy will be large enough, that electric field will be large enough that you can actually cause dielectric breakdown, especially if you get them really, really close together. So that's the sort of relationship between capacitance and voltage.
Okay. And the next question is more really of a marketing question. What do you think about the future of capacitors? What is the trend nowadays? Aluminum electrolytics versus ceramics, films, etc.
That's a great question, and we're actually going to punctuate this whole entire month of so-called basics with a presentation from our Chief Technical Officer, Phil Lesner, that will get into the future of capacitors and a little bit into the future of passive components and what's happening. From a dominant technology standpoint, obviously ceramic capacitors by volume are the leading capacitor types. But it's really hard to say because it all kind of depends on the application. If you're talking low voltage, portable, mobile electronics, consumer type of stuff, battery driven things, that's generally going to be a ceramic capacitor play, and the use of ceramic capacitors in those applications and those systems is going to increase more than the use of other technologies. But if you're looking at things like really high power systems, really high kVA type of things, kilowatts, hundreds of kilowatts into the megawatts, ceramic capacitors have a much weaker play there and are more in the film and electrolytic place. So it really depends on the application of it and what type of trend and vertical market you're looking at. So it's hard to say that one is really gonna dominate. Of course, if you're just looking pure volume numbers, like we produce, I think it's like 50-something billion capacitors a year. The vast majority of those are ceramics. Okay.
And I think we have a couple of more minutes for questions, Wilmer.
Let's take it for another minute or so, and then we'll wrap up.
Okay. So what is DC bias?
Oh, DC bias. So we'll get into that a little bit. in the follow-up to this on ceramic capacitors, but DC bias is a capacitors, and very specifically class 2 ceramic capacitors, phenomenon that they will lose capacitance due to applied voltage. So that actually comes from the fact that, back to these dipoles here that you see on the screen, in a class 2 ceramic capacitors, when you apply DC bias to it, you're almost, let's say, locking some of those dipoles in place, and they have less of an ability to line themselves up with that electric field. So those dipoles that are now locked in place are no longer able to act as part of the capacitor. I mean, I'm going to make up a word here, but they're no longer able to capacitate, if you will. Think of it that way, because they're locked into place. So they no longer serve as an element that adds to the capacitance.
Okay, and we do actually have a good level of engagement, so there's still more questions keep coming in, but I think this will be our last one.
Oh, this one, the last one, David, and then you know, we're trying to get everybody back to work in a sense.
Okay. Yeah.
We'll please submit them. Actually, let's get them in through the Q&A window, and also submit them through the form that I'll show at the end of the presentation here. We'll try to get to as many of those as we can. It's great that we have this engagement.
And how about if I answer this last one, Wilmer?
All right, give it a go.
All right, so will you be doing something similar for inductors? And the answer to that is absolutely yes. I'm actually the one who's going to be presenting our inductor basics webinar on June 15th. That is 2 Mondays from today. So with that said, we'll wrap it up for today, unless, Wilmer, you have anything else to add?
Yeah, I just want to finish up with just a little bit of what you mentioned before. Yes, in our upcoming webinars, on Wednesday, June 3rd, we have, so Wednesday of this week, we're continuing our basics series, ceramic and film capacitors. On Monday, we're going to pick it up with the basics of tantalum and aluminum electrolytic capacitors. And then on Wednesday, June 10th, I'll be back with 2 of our FAEs, and we're going to be dispelling the top 5 capacitor myths. We're going to be discussing what those top 5 myths are that our FAEs have seen in the field, and some of these things that they commonly answer. So be sure to register for those. And as David said, if you have any other questions, submit them through this window, and we'll get to as many as we can, and we'll get to as many as the unanswered ones that we got on the Zoom meeting. So with that, thank you very much for attending. I'm Wilmer Companioni, and I'll be seeing you at a webinar in the future. Thank you, everybody.
Thank you. Thank you, Wilmer. Thank you for attending. Have a good day and be safe.